Hi everyone, we're back to talk about the derivative some more. So in the last lesson, we introduced the concept of the derivative. That lesson didn't really have a lot of examples, but the ones that it had were pretty important. We went kind of in depth about what the derivative means, so make sure you're familiar with that. And in this lesson, we're going to look at some more examples. We're going to look at some different functions and find the derivative of them. And we're also going to ask ourselves, is it possible to talk about the derivative without having a specific point of interest? Can we just have a function and say we're going to find the derivative in a broader sense? So that's part of what this section is about. Okay, let's go ahead and start doing that. So this section is called the derivative as a function. And I want to remind you what we did last time is we arrived at this formula. I'm not repeating the entire definition, but we said that the derivative of f at x, it's denoted in this way. We pronounce this f prime, and it has a formula that you're going to need to know. It's the limit as h goes to 0 of f of x plus h minus f of x, all of that over h. Okay, so we're going to use this a lot today. So if you don't have this formula memorized yet, hopefully you will have it memorized by the end of this video, because we're going to use it a few times. How about this? Something that just occurred to me. I don't think I said this in the previous video, but some of you may have looked at this and said that this expression might look familiar to you from algebra classes or from a pre-calculus class. Have you ever had an algebra class where you were given some kind of function and then you were asked to simplify something that kind of looked like this? If you were, if you ever saw something like that, it might have been referred to as the difference quotient. The difference quotient. Anyway, sometimes we give algebra students questions like that where you're simplifying, you're just working, there's no limits because you don't really have calculus yet. So without the limit, but you're just kind of simplifying expressions that look like this. And we give those to algebra students to help prepare you for this moment, to help prepare you for calculus, because the derivative is based on this formula. Okay, so that was just a little side note. If you've seen this sort of expression before, it's not just a coincidence. We give those to students for algebra practice so that you'll be able to do algebra once you get here. I'm going to say we can use this, meaning we can use this formula if we're given a specific value of x. And in the previous section, we had a specific function, f of x was x squared, and we looked at it with x equals 1, and I think we looked at it with x equals 3. What's new for us now is otherwise. Otherwise, what if we're not given a specific value of x? Well, in that case, we just leave x as a variable. So instead of having a specific point of interest, like x equals 1 or x equals 3, we're just going to say x is a variable. Just leave it as x. And let's see what happens. So I want to start with f of x equals x cubed. This problem is going to say, let's find f prime of x. And I'll walk us through this. After we do this one, I'm going to have one for you to try. Do we know how to do this? Let's see. Well, we want to use the formula that's above. Let's just start using it and see what happens. F prime of x, it's supposed to equal the limit as h goes to 0 of f of x plus h minus f of x, all of that over h. And, you know, if this formula is new to you, one thing that I would suggest is each time you do one of these problems, go ahead and write the formula down. I think that's a really good way to memorize things, is every time you use the formula, write it. And after you've done 5 or 6 of these, you write the formula down 5 or 6 times, you'll find that you just get used to it, and then it's a good way to remember it. Let's actually put in the specific function that we're dealing with. So instead of calling it f, we know what it is. It's x cubed. So what's f of x plus h? Well, x plus h cubed. What is f of x? It's x cubed. And it's all over h. Before I go any further, I want to make sure everyone understands this step. Went from this to this. I wish we were in person right now because I would ask if anyone has questions about it, but take as much time as you need to review what we did here. You could do a little scratch work if you want. You could say, scratch work. F of x equals x cubed. So, f of x plus h is x plus h cubed, right? Whatever you put into the parentheses, whether you're putting in x, or you're putting in x plus h, or if you're putting in a number, whatever you put into the parentheses needs to get cubed. If you just put in x, it's x cubed. If you put in x plus h, it's x plus h cubed. The cubed is on the outside of these parentheses to make sure that x plus h is being treated as one object, and that entire object is getting cubed. Side note, x plus h cubed does not equal x cubed plus h cubed. That would be a big algebra mistake. Okay? In fact, I think that algebra mistake is, it has a name. It's so common that it has a name. I've seen it on Wikipedia. It's called freshman's dream. Or maybe it's called sophomore's dream. No, I think it's called freshman's dream is the name of this algebra mistake. It's like you wish that this equaled this, but it does not. What does x plus h cubed, what does that equal? It equals x plus h times x plus h times x plus h. And then maybe you need to do like a little bit more work to figure out what that equals. You do all the distributing, right? You could also memorize a formula for how this all expands. Some students do that, but this is what it does equal. That was all kind of side note and scratch work. I wanted to make sure we understand how we're getting to here. Let's go to the next line, and I've expanded the x plus h cubed. You could do all this work if you need to, x times x times h times, add it all up. You get x cubed minus 3hx squared plus 3h squared x plus h cubed. That is the expansion of this. And then you still have minus x cubed. That's the minus x cubed that was already there. And it's all over h. Now, if this problem is going to work out kind of anything like the previous problems we did in the previous video, then we're probably going to have some things cancel out. And look at this. We do. There's an x cubed minus x cubed. Cancel those. Did I write a minus that should be a plus? I think I wrote a minus that should be a plus. Let's fix this. Some of you might have noticed that. I don't know why I wrote this as a minus. This is going to need to be a plus, okay? Because everything that we're dealing with here is plus. We have a x plus h. Sorry about that. This is a plus sign. The only minus sign involved is the minus x cubed that was already there. Okay. Okay, so what I want to do next is notice that the pieces that are still here, they all have h. So we could factor an h out of the top. Notice that as I do this, I'm starting by writing equal sign limit h goes to 0. You need to do that. You need to write equal signs between things that are equal. You need to write limit for things that are a limit. If you want to get full credit, you need to do those things. Okay, pull out h. You know, because we want you to write things in math classes here. We want you to write things on paper that are correct. And if there's no limit written here, then it's not correct. If there's no equal sign, then what you've written doesn't mean anything. I had a little mistake there where I had a minus sign. You know, I caught it and fixed it. Everybody makes little mistakes like that. You'll see me make other mistakes throughout the semester. The thing is, when you make a little mistake, try to catch it as quickly as you can. We have h over h. That's good, because those are going to cancel. That's going to leave me with the limit, as h goes to 0, of 3x squared plus 3hx plus h squared. Now let's think about what this equals. As h goes to 0, I would say this part of it goes to 0. As h goes to 0, I would also say this part of it goes to 0. And we're going to be left with just the 3x squared. And that is my answer. Now, is that the type of answer you were expecting? I think that in the previous lesson, we were getting answers like 2 or 6. We were just getting answers that were numbers. And this time we're getting an answer that has x in the answer. But this makes sense because we didn't use a specific value of x. We didn't plug in a specific value of x. So we left x as a variable throughout this entire process. And that means by the time we get to the end, there's still some copies of x floating around in the answer. Okay, so answers often involve x. I'm going to say, however, the answer should not include h. So you don't want to see any h's in your final answer. I'm kind of saying this now as kind of a heads up, you know, something to watch out for. All the h's went to 0. Or they either went to 0 or they canceled out in a previous step. So that's what's going to happen. Some things cancel out, some things go to 0. By the time you get to the end of the problem, there's no h's left. There could be x's, though. Now, I have one like this that I'd like you to try. Before I give this to you, though, I want to say I need to address something. Okay, so this is Calculus 1. And, you know, this is College Calculus 1. And some students may have seen calculus in high school. Some students might not. Everyone kind of comes from a different mathematical background. So some of you may have seen this before in like a high school class, and I know what you're thinking. if you've seen derivatives before, then you're probably thinking, when are we going to get to the shortcuts? So I want to address all of you right now and tell you that there are some really good derivative shortcuts coming up. in the next section. So they're not going to be in this video today. For now, when we solve derivatives in this section, this is how we should do derivatives. This is what we know so far in this class. So if you've taken calculus before, just bear with me for one lesson. Let's do derivatives this way. It's good to do it this way to get a good understanding of what the derivative really is. And this is what the derivative really is. But yes, we do have good shortcuts coming up soon. So let me give you a problem, and I'll ask you to solve it using what we've said so far in class. And it's going to be given f of x equals x squared plus x. I'd like you to find f prime. And you could pause the video for a minute and give this a try. Okay, so let's see. I've already written f prime of x equals, and then I wrote the formula for the derivative. Now the next step is we get this function put into place. So kind of like we did on that side work, we need to be careful about putting x plus h into this function. Let's write limit h goes to 0 first, so we don't forget that. And this is, the whole thing is going to be over h. Okay, we need something minus something, right? Something big goes here, there's a minus sign in the middle, and then there's something over here. What is f of x plus h? Well, take the function, and everywhere that x appears, you replace it with x plus h. So instead of x squared, it's x plus h squared. Instead of x, it's x plus h. Now comes my big minus sign. All right, are we good so far? So what I did so far, I'll put a box around this. This part of the problem is this part of the next step. That's what happens when I plug in x plus h. Now I have to do minus f of x, so minus x squared plus x, right? But I am going to put parentheses around it, parentheses x squared plus x, because I want to make sure that the entire thing is getting subtracted. So I either need to put parentheses around it or distribute the minus sign to change this plus to a minus. I'm going to wind up doing that in the next step. I put parentheses around it to make sure I'm subtracting that the whole function. If you've gotten that far, like, I actually think that some of the first steps are the hard ones. If you have this correct, then there's a pretty good chance you're going to get the rest of it right. So what have we done in the previous problems? We usually will expand whatever's in the numerator and then start looking for things to cross out. So I'm going to expand like this x plus h squared gets me x squared plus 2h x plus h squared. And then we still have the plus x, the plus h. Now I'm going to distribute the minus sign here. So look at all that. This is the sort of thing where the numerator seems like it blows up and gets really big. But then in the next couple of steps, we're going to start crossing things out and simplifying. And we'll get a nice, small, compact answer. So what can I cross out? Well, we have x squared, and we have a minus x squared. That's generally how these problems work, is you get to here and you start finding things. Look, plus x, minus x. You find things that you can cancel. That's a good sign that if you know, half of the numerator is canceling, or roughly half of the numerator is canceling, that's a good sign that you're probably on the right track. Now, what does that leave us with? We can write this here. Limit h goes to 0. I noticed that there are 3 pieces left in the numerator, and they all involve h. So I'm going to factor h out of the numerator. Before we go any further, let's double check this step that I just did. We had a 2hx, and I wanted to pull h out. That's where I got 2x. We had an h squared, and I wanted to pull out h. So that's why I have an h on the inside here, and an h on the outside. We had plus h, and I wanted to factor h out of it. So we have an h out here and a 1 on the inside. Because if you were to distribute the h into these parentheses, you would get the 2xh plus h squared plus h. So this all checks out. We're just checking that, yes, these two things are equal to each other. If we're good with that, then let's go ahead and cancel h over h. That seems like that's been happening in all of the problems we've had. So we get to limit h goes to 0 of just 2x plus h plus 1. As h goes to 0, what happens to each piece of this? As h goes to 0, 2x is still just going to be 2x. There's no h's in there, so 2x is just 2x. The h, however, is going to be gone. That's going to be a 0. What happens to 1? As h goes to 0, the constant 1 is still just the constant 1. So my final answer to this is 2x plus 1. And there are no h's in the final answer. So earlier I was saying that there are going to be some good derivative shortcuts, and there are probably, a couple of students who've seen these shortcuts before. I guess I could say that if you know the derivative shortcuts, you could use them to check your answer. There's no harm in that. But for now, I'd like us to be doing this this way. By the way, the title of this section was the derivative as a function. And you notice that each time we've done these, we find the derivative f prime of x. What we're actually getting, the answer is actually a function of x, like 2x plus 1. So this problem gave us a function. F of x is x squared plus x. That's a function. We found that f prime of x is also a function. We might talk soon about how these two functions are related to each other. What else can we say? Well, let's also talk about what can this do for us. In the previous video, the previous lesson, we were using specific values of x. And what was nice about that is it was telling us the slope of the tangent line. It's a measure of how rapidly the curve is changing, the rate of change. So I've got a little follow-up question here, and I'm going to talk us through this follow-up question to the one we just did. Let's say we're given that same function, and let's say we want to find the slope of the tangent line when x equals 5. Now, I'm going to answer this for us. It's going to be pretty quick. This is kind of how we phrased the questions in the previous video. In the previous video, we were given a function, find the slope of the tangent line at a certain x value. Okay? Now, we found f prime of x was 2x plus 1. So I want to show you that this actually works as kind of a shortcut for answering this type of question. Since f prime of x is 2x plus 1, that means that f prime of 5 is 11. Done. I put 5 in. I put 5 in to 2x plus 1. What if you wanted to know the slope of the tangent line when x is 7? Just put 7 in. Put 7 into 2x plus 1. If you want to know the slope of the tangent line when x is 100, put 100 in for x. So what's nice about doing the derivative in this way, in this like general way where we leave x as a variable, what's nice about it is you can very quickly get the slope of the tangent line at any x value you want, and you don't have to redo the problem for each x value. You could say, slope of the tangent line at 5, boom, done. So that's pretty cool. But of course, that's only because we already did the work to get the 2x plus 1. All right, now the derivative is still kind of a new concept for us, so I have some notation to tell you about. Notation, definitions, facts. So if we're given y equals f of x, the derivative of f can be written in any of these notations. I'm going to say that we've only said one of them so far, but in fact there are going to be 6 of them here. Here's one of them, f prime of x. We know that that is notation for the derivative of f. I'm going to tell you now some other ways that we can write it. Another way you could write it is you could say y prime. Y prime. It makes sense that you could do that because y equals f of x. So instead of putting the prime on the f, put the prime on the y, and it means the same thing. Another way that we sometimes do this is, this one's going to seem a little different, d over dx f of x. And there's no prime symbol. There's no little markup there. There's no apostrophe looking thing, no prime symbol. D over dx f of x. This notation means the derivative of. This is like saying the derivative of f of x. You could also do d over dx y. The derivative of y. And the x here, when it says d over dx, the x is telling us that x is the variable. Maybe later we might have some other things where there's like a different variable. I guess like in the previous video and this video, the variable has been x the whole time. What winds up happening later is maybe you get some word problems or something where maybe the variable is t. Like if it represents time, sometimes the variable is t. And in that case, maybe there'd be like a t that shows up in one of these, but it's usually x. There's 2 other ways. The one that I'm going to write up here in the upper right is probably the one that we use the least often, but I want to tell it to you anyway, just in case you see it. And that is df over dx. Kind of similar to that previous one, the derivative of f. And finally, the last one, and this is one that we will use this one a bit, dy over dx. So that's 6, the derivative is such a common thing to talk about that there's 6 different ways to write it. There might be other ways as well. I want to say something about, well, first of all, let me tell you like which ones are the most common for us to use. I guess the first one, the y prime, the last one we'll use. I think that these middle ones we're also going to use. I feel like the one in the upper right is the only one that doesn't really get much attention. Let me say this last one, dy over dx, there's two things I want to say about it. The first one I'm just going to say out loud. I'm not going to write it. I want to tell you that when we see this, the way that we pronounce this, we often will pronounce this as dy dx. dy dx. We often don't say the word over. dy over dx? No, we often just say dy dx. And from the context, it's clear what we're talking about. These ones over here, these are often pronounced d dx. I know that seems weird. Like, why aren't we saying d over dx? It's just kind of the standard convention. So if you ever hear me say, you know, what's d dx of y? It means this. Okay. The other thing that I wanted to say about this, in particular, this last one, I want to say that this looks like, it looks a little bit like slope. Remember, slope was like the change in y over the change in x, which I said was often represented with the triangle, which is the Greek letter delta. Delta y over delta x. Now we're saying dy over dx. It's not just a coincidence that that looks like slope. It looks like slope because it is the slope of the tangent line. All right, let me tell you, just for example, with this notation we found earlier, we found the derivative of x squared plus x, and another way that we could write it is d dx of x squared plus x. We found that it was 2x plus 1. We also found that d dx of x cubed was 3x squared. Okay, so that's d dx of something equals something. So it's like the derivative of this equals this. Another little bit of terminology, I guess, is the process of finding a derivative is called differentiation. You might say we are going to differentiate a function. Got some more terminology for you. We say f is differentiable at a if f prime of a exists. Oh, well, that kind of raises a question, doesn't it? That kind of raises a question of like, wait a second, are you telling me that that means sometimes a function is not differentiable? Sometimes a derivative does not exist? Well, let me remind you. What is the derivative? Let's go back. First page from today. Here's our formula. We're working on memorizing this formula, right? It's all about a limit. And we know from the sections that we had about limits, we know that sometimes limits don't exist. So if sometimes a limit doesn't exist, that means sometimes the derivative is not going to exist. If it does exist, we say the function is differentiable. Let's talk about some cases. I'm going to tell you 4 cases. 4 cases when f is not differentiable. I'm going to say that in calculus, we hope that for most of the functions that we look at, they will be differentiable at most values of x, or most values of a. So it's really just going to be certain problem points, certain problem areas where something might not be differentiable. Okay, let's try to leave room for 4 little sketches. They don't have to be big, just we're going to get the rough idea. All right, XY axis. How about this? While we're writing all this, can you think of any? Can you think of any cases where you think a function might not be differentiable, where the derivative might not exist? There's 4 of them, so you might be able to think of some of them. And what would they look like? So if we were doing this in person, I would get some answers from you. I'm going to list 4 different ways, and of course, you might come up with these in a different order. Remember that the derivative ultimately is telling us the slope of the tangent line. What I want to say is one place where a function might fail to be differentiable is if the tangent line is vertical. Underneath, I'm just going to say vertical tangent line. Because what is the slope at that point? The slope of a vertical line is undefined. So the derivative would wind up being undefined. So that's one case. Another case that is kind of similar in a certain sense is if we had a sudden vertical jump. So if I had a piecewise function maybe, and I looked, at this x value, and I said, what is f prime of x at this x value? Well, what would the tangent line even look like? We can't really define the tangent line in this case. We just say that f is not differentiable because there is a discontinuity. Remember, a discontinuity is somewhere where a function is not continuous. All right, next one. The next one might be a little surprising. I'm going to use a specific function. I have a specific function in mind here for this example. Hey, do you know what function this is? Do you recognize that? That is y equals the absolute value of x. Now, what is happening at 0, 0 for this function? What if I asked you to find the derivative f prime of 0? What's the slope of the tangent line at 0? So here's the reason why this is going to fail to be differentiable. It's because if we look at the limit from the left and we look at the limit from the right, not just the limit of the function, but the limit of the derivative formula. Okay, we're trying to get the slope of the tangent line, and as I go from the left, I think the slope looks like it is -1. Right? Keep going this way. If I go from the other direction, the slope of this part looks like it is +1. Goes like that. So is the slope of the tangent line -1, or is the slope of the tangent line +1? Well, it can't be both of them, and we say that the derivative here does not exist. And the thing that's causing us the problem is the sharp corner. Anytime you have a sharp corner, at that point, the derivative doesn't exist. So that's an interesting one. Luckily, a lot of the types of functions that we deal with in calculus and pre-calculus, a lot of functions we deal with don't have sharp corners. You know, you think about polynomials that wave up and down in a nice, smooth manner. You think of exponential functions, logarithmic functions, you know, maybe trig functions. Do trig functions have sharp corners? Sharp corners don't come up too often. But when they do, that could be a not differentiable case. The last case is actually going to be pretty simple. I'm going to use another function that we know. I'm going to use y equals the square root of x. And I'm going to say, what if we looked at this? What if we looked at it over here? What if we had a function where the domain does not include these numbers? And what if I asked you, what is f prime of -2? Okay, well, f of -2 does not exist. And it turns out that f prime of -2 is not going to exist either. I will remind you again, this formula that we are working on memorizing, formula for the derivative, it has f of x in it. So f of x has to be defined in order for it to go into this formula. You know, if f of -2 is undefined, so we can't put it in there. So this is basically the case where f is undefined. If f is undefined, then f prime is also undefined, and the function is not differentiable there. This function can be differentiable somewhere else. 1, 1, yeah, it's differentiable there. Pick some other points on this curve. It is differentiable on all of those places. It's just not differentiable here. Okay, let's move on a little bit. So we've seen some notation, some terminology, cases where something is not differentiable. I've got a little bit of extra notation for us. So if we're given y equals f of x, the notation dy dx means f prime of x. Now that sentence right there is not really anything new. We said that on the previous page. And, okay, now this next part is going to be new. This is going to be kind of a variation on the dy dx notation. Dy dx with a vertical bar next to it, and at the bottom of the vertical bar it says x equals a. I need to tell you what that means. It means f prime of a. And you might be thinking, well, why don't we just say dy over dA? Like, why can't we just put the a on the bottom? Why do we need something complicated like this? The reason why we need it to look like this is because the dy dx notation is there to tell us that y is the function and x is the variable. So we do need the x down there to tell us that x is the variable. And we basically find dy dx, and then after we have found it, then we plug in a. It's kind of like we did that earlier when we had something where I found f prime of 5 Like we already found f prime of x, and then I plugged in 5. It's kind of like that. You find the derivative, and then afterwards you might plug in a specific x equals a. So here's a little example, just to get used to this notation. Let's say we're given y equals x cubed. Okay? The notation dy dx vertical bar x equals 2. Let's talk about what that means and what that equals. It means, I'm going to use some quotation marks here. It means, quotation marks, dy dx evaluated at x equals 2. And I think earlier we found the derivative of x cubed earlier. It was the first example that we did in this lesson. We found that it was 3x squared. So this means 3x squared evaluated at x equals 2. So if I just said to you, hey, what's 3x squared evaluated at x equals 2? You would put the 2 in for x, and you'd get 3 times 2 squared, and it equals 12. That's all there is to it. The trickiest part of this is just the notation looks weird, but if you're careful and think about what it means, it makes sense that the answer to this was going to just be a number, because we're actually plugging in a specific value of x. In fact, this would be the slope of the tangent line to this curve at x equals 2. So we just found it. So we've been talking about the derivative in this lesson, and I think we're able to find f prime for some functions now. I want to show you a different type of question. I want to show you that there could be a question where you're just given a graph, and some questions could be asked about the derivative. So given the graph of y equals f of x, I'm going to say visualize the tangent line to find the following. Now, give me a moment to draw this. Make sure I can draw this function right, because this is giving us the picture. We're not going to have a formula for f of x. And I kept saying that there's this formula for the derivative that you want to memorize. So can we find a derivative without having a formula for f? We'll see. Okay, that turned out pretty good. So now I'm going to ask 3 questions about this. I'm going to ask you to find dy dx. All right, to find that. Find that. And to find that. All right, so I'd like you to take a minute and see if you can figure these out. You could pause the video if you'd like. See if you can find this based on the graph. So when I say visualize the tangent line, you could draw it if you want. Draw some, like I was using a blue pen. You could use another color if you want to try to do that. Let's see here. Also, what does this notation mean? dy dx evaluated at x equals 0. So this is really asking us for f prime of 0. This is asking us for f prime of 1. And that's not the answer. I mean, we still need to say what it equals. This is asking us for f prime of -1. I'm just writing it in both notations. And we were told that this function is y equals f of x. So I'm not going to use the derivative formula because I don't have a formula for f of x, so I don't really think that would help us. Let's look at what's happening to this function around x equals 0. Okay, here's 0. Here's 0. Here's x equals 0. What's happening on the curve, though? The curve is up here. Can we visualize the tangent line? Now remember, the tangent line is supposed to kind of just graze the curve at that one point, following the same sort of trajectory or curvature or steepness. I think that here it actually looks pretty flat. Like I wouldn't really draw this line going upward or downward. I think we're kind of like at the top of this hill, kind of balancing. Like maybe the tangent line looks something like that. And then I ask myself, okay, if that's the tangent line, what is the slope of this blue line that I drew? Can I approximate the slope? That's a horizontal line, so I think the slope looks like it is 0. I am going to say, for this one, my answer is 0. That's the first time I think we've gotten an answer of 0 to one of these. But if the tangent line is horizontal, which it could be, if the tangent line is horizontal, slope of it is 0. How about the next one? It says x equals 1. So we're looking at a different part of the curve. We're looking here. This is x equals 1. So what is the curve doing? I'm going to try to draw the tangent line again. So the tangent line should be a straight line that wants to pass through that one point and kind of follow the direction of the curve, even though the tangent line itself is not curved. Maybe something like that. Here, I'll zoom in on this. Can you see that? I drew a blue line going like this. Can we figure out what the slope of that blue line is? Well, yeah, I think there's a couple of ways. I mean, you could find 2 points on this line and find the slope that way. You could say it looks like it's making a 45-degree angle with the x-axis. That kind of tells me something. You could say for every 1 unit I go to the right, it looks like I'm going 1 unit down. That is exactly what a slope of -1 looks like. And I'm going to say the answer is -1. I think that's the first time we've gotten a negative answer for one of these, but that's okay. If you're going downhill as you go from left to right, you're going downhill, you were at the top of the hill and then you just start rolling. You're rolling down this hill, or maybe you're on a sled. Slope would be negative as you go downhill. And finally, the last one is asking us about what's happening when x is around -1. So that's this part of the curve. Oh, you know what? This kind of looks familiar to me. This looks like one of those, we had 4 cases where f is not differentiable. This looks like one of them because the tangent line here that I was going for, if I drew this just right, the tangent line is vertical. So what's the slope of a vertical line? Undefined. So that is a possible answer for these types of questions. The answer could be undefined. Slope of a vertical line. All right, so we've still got a little more to go for this section. We're not finished yet. I just thought I would stop in and I was actually just taking a quick break myself. As I record these, sometimes I'll just, pause the recording, take a little break and, get some water or get some tea or something like that. I just thought I would take a break and I wanted to say, I'm giving you a lot of videos to watch this semester, and some of them might be kind of long. So don't forget to take breaks. Don't forget to rest your eyes. I know some of you are probably just thinking like, whatever, let's just get back to this and get it over with. But it's good to take breaks. Give your eyes a rest. Give your brain a rest, especially if you're taking like other online courses too. If you're at the computer all the time, it's good for you to get up and stretch, get some water, and rest your eyes every once in a while, because I'm doing that. So I just thought I would remind you that you should do that as well. Okay. That's one of the nice things about pre-recorded videos, is that you can pause it and take a break whenever you need to. Now, back to the derivative. All right, where were we? We've got, the last section that we did and this section. We're establishing a lot of terminology and notation and stuff, and we've got a little more. So, note, we've been using the word differentiable. We say it's differentiable at x equals a if the derivative exists there. Well, we say f is differentiable on an interval if it is differentiable. I bet you could just finish this. You could finish this definition without me, right? If it is differentiable at every number in the interval. What does this remind us of? It's kind of reminiscent of when we talked about continuity, when we talked about how a function can be continuous at a specific x value. But we could also say a function is continuous on an interval, right? Here's an example for you, quick example. I'm going to tell you, I'm not really proving this to you right now. Proving this would be a different story, but I'm going to tell you that f of x equals x squared is differentiable on this interval. The slope of the tangent line exists everywhere for that curve. So that means that it is differentiable at x equals 0, it is differentiable at x equals 1, at x equals 2, at x equals 2.5, at x equals 3.7. Any real number you put in, that function is differentiable. And you might say, like, we had a theorem when we had a section on continuity. We had a theorem that said this function, because it's a polynomial, it is continuous on its entire domain. And you might be wondering, like, is there a connection between being continuous and being differentiable? And there is. There is a connection between the two. So theorem 1, if f is differentiable at a, then f must be continuous at a. We're not going to prove that. That would actually be tricky for us to prove in this class. I think some of these statements, I feel like some of these statements we prove in a later math class that's called real analysis. But anyway, we can still appreciate what this is saying. If a function is differentiable somewhere, then it must be continuous there. I feel like that naturally leads us to a question. My question is going to be, does this also work the other way around? If f is continuous at a, must f be differentiable at a? So think about it. Think about this for a second. It's a yes or no question. Sometimes in class, I ask for a show of hands of like how many people think yes, how many people think no. The answer to this is no. The answer to this is no. And I will show you why. We've already seen some cases where a function is continuous but is not differentiable at a. In fact, one of them, I don't even have to move the page much. Right here, this vertical. When it went vertical, it's still continuous. You can draw this curve without lifting your pen. There's not a discontinuity there, but it was not differentiable there. So the answer to this overall is no. F doesn't have to be differentiable just because it's continuous. Another example of why that's no was the absolute value example. When we had a sharp corner, this is continuous. You can draw this whole V-shaped function without lifting your pen. There's no discontinuities. It's continuous, but it's not differentiable at the sharp corner. So if a function is differentiable, the theorem says it must be continuous. But if a function is continuous, it might be differentiable or it might not be. It depends. What I'd like to do for the rest of the section is have us do some more examples of differentiating by using the formula from the definition of the derivative. That's kind of enough theorems for now and enough terminology for now. Let's do some more problem solving. So I have one that I'm going to do myself, and then after this, I'll have one that I'll ask you to try. First of all, let's find... I'm going to try to use this notation a little bit to get so that we get used to it. Okay, I'm going to do this one for us. We're going to find this. That's the question. That's the whole problem. And I'm going to do this one for us. But what does this mean? Let's try to remember what this means. This means given f of x equals the square root of x, find f prime of x. Okay, that is what this is saying. It's just written in a different notation because it says find the derivative of square root of x. So now that we have that in mind, let's go ahead and use the limit as h goes to 0 of f of x plus h minus f of x over h. And I'm going to go ahead and put in the square root of x is the function, so f of x plus h is the square root of x plus h. And f of x is the square root of x. So this is where we're at. So where do we go from here? You know, this looks a little different from other problems because I guess in the other problems we had like polynomials for a few examples, and then we had like something in the numerator that we could expand and then look for things that cancel. This one looks different. Luckily, we've seen things that look a little bit like this back in our lessons about limits. We had limits that had square roots in them, And we're going to use the same kind of trick. We are going to use the algebra trick where we multiply by the conjugate over the conjugate. So you change to a plus sign, same thing on top and bottom. Multiplying by the conjugate over conjugate is going to wind up helping simplify this. The algebra is going to work out. So limit h goes to 0. Let's distribute the numerators and see what happens. In general, multiplying by conjugate over conjugate does help you simplify things that involve square roots. So the square root of x plus h times the square root of x plus h is x plus h. Square root of x plus h times square root of x looks like this. Minus square root of x times, okay, so minus square root of x times square root of x plus h. And then the last terms, minus square root of x times plus square root of x. That's going to give me a minus x. That is my entire numerator. For the denominator, I'm going to pretty much leave it the way it is with the h on the outside and this other stuff in parentheses. Now, I promised that this was going to make things simpler. And you might look at it and say it looks complicated. But check this out. We've got things that cancel. This minus itself cancels. We also have x minus x. That cancels. In fact, what's left? What's left in the numerator? Is there anything? There's only h. There's only h. So if the numerator only has h and the denominator has h, we could cancel the h over h, right? H over h cancels to be 1. So let's do that. Limit as h goes to 0. The new numerator is just 1. Okay. At this point, I want to use some limit properties. And we had a lesson on limit properties pretty early on. And, you know, we could say it's okay to take the limit of the top, limit of the bottom, limit of each piece. You're allowed to pull square roots out of limits. Remember all those properties? It's okay with me if you want to apply a few of those properties all at once. Because once we get to here, I can kind of tell what's going to happen. This is going to equal, using limit properties, this is going to equal 1 up top, and the bottom is going to be x plus 0. That's what's going to happen. To the limit of h goes to 0, it's going to become this. And one more step, and we'll call it a final answer. X plus 0, of course, is just x. So I have a 1 up top. How can I simplify the bottom? Square root of x plus square root of x is 2 square root of x. And that's my final answer. So this problem was probably a little tougher than some other ones, but it's because there were square roots involved. It wasn't just a polynomial. But yeah, everything checks out. So if you needed to know, by the way, if you needed to know, like, what's the slope of the tangent line to the function f of x equals square root of x at some x value, you would put it into this. All right, I've got one for you to try. I'm going to ask you, I'm using the word find. Besides the word find, we could also use words like, we could say compute, we could say evaluate, we could say differentiate. I would like you to work on this and see if you can simplify your answer. And I'm going to, suggest that you pause, take a couple of minutes, and give that a try. All right, so I'm going to start by saying that the derivative of 1 over x is following the derivative formula, f of x plus h minus f of x over h. And you might look at this problem and say, well, wait a second, this problem doesn't even have anything called f. This problem doesn't actually give us f. But when I write this notation, I'm using f of x equals this. Okay, we did that in the previous problem too. That's the function that we're interested in. Limit h goes to 0. So f of x plus h is going to be this function, but everywhere that x appears in the function, I'm going to replace it with x plus h. So I get 1 over x plus h minus 1 over x. All of that is over h. We've got some simplifying to do. Got fractions inside fractions. What are we going to do about this? Probably a couple of different ways you could handle this, but I think what I want to do, I'm looking at the numerator. Let's just focus on like what's going on up top. Let's leave the h on the bottom for now, and just the parts up top, fraction minus a fraction, and it would be really nice if they had the same denominator. So let's find a common denominator. How about that? You know, generally, like when you want to do a fraction minus a fraction, like if I said to you, what's 2/3 minus 1/4? A lot of times you would find a common denominator. So what's 1 over x plus h minus 1 over x? Do a common denominator. Common denominator, actually, that would work really well is x times x plus h. So here, I'm going to set this all up. All I did is multiply the two denominators times each other. We're going to put something up here. You can always do that. Multiply the denominators. It guarantees you get a common denominator. It might not be the least common denominator, but it's common. So what do we do up top? We had a 1 up top. This is going to be x. And what goes here? This is going to be x plus h. Next step. You know, sooner or later, we're going to have to do something about the h on the bottom. We could do this now, or we could save this for later. I'm going to go ahead and do it now. I'm going to say that the h on the bottom, let's just make it a 1 over h out front, like that. I'm not allowed to pull this all the way out of the limit, you know, because the limit as h goes to 0, you can't pull h's out of that. But I can pull it this far to the left. And then what else have we got then? Times the rest of it. The stuff that was up top. So the denominator is x plus h, and I'm merging this into one fraction now. That was the whole reason why we got a common denominator. X minus x plus h. So distribute the minus sign. X minus h. Be careful about pluses and minuses. Right now, I have a fraction times a fraction. We're mostly just doing algebra, aren't we? Like, it feels like that's all we're doing today is algebra. Let's fraction times a fraction. Let's just make it one fraction, right? hx. And then what's up top? X minus x is gone. All that we're left with up top is minus h. You know, maybe I should be going through some of this algebra faster because this is calculus. We should be good at algebra by now. H over h is -1. You know, there's a negative h up top, negative h over positive h, -1. And then what can we do here? How about we expand? I decided to expand what's in the denominator here. -1 up top, x squared plus hx. And now let's use some limit properties, okay? H is going to 0. What happens to the numerator? Numerator stays -1. What happens to x squared? X squared is x squared. What happens to hx? The hx part of things, that's going to go to 0 because h is going to 0. So what I am left with as an answer is -1 over x squared. That's my final answer. That was a big problem. That kind of took up the whole screen. But when you look at this, I would say almost the entire problem is spent simplifying things. It's kind of like we get the answer pretty early on, and then we just spend the whole time simplifying it. Which is mostly algebra and being good with fractions and stuff like that. So this is good. We're starting to be able to find derivatives of lots of different types of functions, not just polynomials, right? We've done some polynomial ones like x squared, x cubed, x, stuff like that. But now we can do 1 over x. Earlier we did the square root of x. How about we do one more? One more. I had this in my notes as like an extra problem for, if we have time, let's do this extra problem. So I'm going to ask you to try this one. I'm going to ask you to compute d dx of x squared minus 3x. So this is another place that would be good for you to pause, try this one on your own, and then you can compare your answer with mine. So let's get started on this. D dx of this function equals limit h goes to 0. Remember earlier in this video, I suggested that if you've got this formula and you want to memorize it, it would be a good idea to just write it every time you use it. And I said that after you write it 5 or 6 times, you'll start to just know it. So hopefully that's happening. Just write the formula every time. And when you do homework problems, and by the way, let me be clear. If you skip writing this formula, I'm not going to take points off. It's just a suggestion that at this point in the course, it would be a good idea to write the formula as many times as you need to until you've got it memorized. Okay, so we'll go through this one a little faster because I've been spending a lot of time on, algebra stuff that we should be good at. F of x plus h is x plus h squared minus 3 times x plus h minus x squared minus 3x. Notice the parentheses that I put there. You need to either put parentheses here or distribute the minus sign. But I'm going to put parentheses and then distribute the minus sign in this upcoming step. I'm going to expand the x plus h squared, so x squared plus 2hx plus h squared minus 3x minus 3h minus x squared plus 3x. All of that is over h. Okay. Generally, we'll start going faster with problems once we've spent some time on them going slow. We can speed up now. We want to cancel stuff, right? Hopefully we get to this point in the problem and there's some things that cancel. We have x squared minus x squared, and we have a minus 3x and a plus 3x. Good, good. That seems to suggest to me that we're on the right track. Everything that's left in the numerator has h, so I'm going to pull h out of the numerator. That's going to leave me with h over h, which is going to cancel. Get rid of those. H over h in this case is 1. Limit h goes to 0 of 2x plus h minus 3. We're taking a limit, so the h part of it goes to 0, and I'm left with 2x minus 3. So that was just another good practice problem. Probably not the hardest one that we did. All right, and you'll probably see some more things like this in homework. So this was a big section. This was an important one. When you think about it, though, really, most of this section was just about using the derivative formula to find f prime of x. We've done that now for x cubed. I think we had something that was like x squared plus x. We did it for 1 over x, square root of x, and that last one was x squared minus 3x. So we've done a bunch of problems. We also had some other types of problems. We had one where we were given a graph, and it was asking us about the derivative based on the graph. And you can do that as long as you understand what a tangent line is. Yeah, so I think we're doing well. I did mention something in the middle of this lesson about shortcuts that are coming soon. So if it feels like we're just getting buried in endless amounts of algebra, there are some nice derivative shortcuts on the horizon that'll be here before you know it, and it'll skip some of the algebra steps for us. So that's really nice. Okay, so that's everything, and I'll see you next time. Make sure you don't miss the next video. I think it's a very important one. I'm probably going to be saying that every video for the next few videos, but like, we're learning the fundamentals of derivatives right now, and you're not going to be able to succeed later in the course unless you really get these fundamentals down. Okay, so watch the videos, do practice problems, do homework problems, and ask me questions when you get stuck on something. Okay? All right, take care, and I'll see you for the next video.